Hello, welcome back. We only have 17 people. I guess that's because we don't have quiz today. Yes, lovely Wednesday. All right, so before we start, I want to say something about your homework 5. Although we only have 17 people here, but I'm sure I hope all of you will be watching this recording. For your homework assignment 5, we did not usually have that appendix. We do have the appendix this time to help you go through the implementation process, but I do not want to answer questions about the appendix because I don't want it to be a homework assignment that you follow some instructions, you implement step by step to finish the assignment. That doesn't really make much sense, right? If people ask you about, say, k-means, okay, why are you implementing k-means following an instruction? You can already use all the libraries to implement k-means. So what do you want to learn based on the assignment? I want you to use the assignment to try different thresholds, look at the data, and see how you would be able to change the implementation, or maybe change the way you compare clusters, compare point to clusters to make it better, right? That's the goal of the assignment, not to ask you implement a k-means algorithm that will be able to scale up. You can use a library for that. So you can still ask any questions you like on Piazza, but if I see a question that I think it's too detailed, you should be able to figure that out. I would just tell you, you should be able to figure that out, okay? All right, so let's continue. So we have two more topics in this course, and today we are going to talk about a very, very cool algorithm, PageRank. PageRank is the algorithm that Google invented and eventually made Google a multi-billion company today. So let me set up my slides. All right, so PageRank and link analysis. Now we are going back to graphs again. It will be very exciting. All right, what is the problem? So say, all our examples will be using web graph like this one, but just to let you know that this PageRank algorithm can actually be used in many applications. We can talk about that, but let's start from graph. Let's start from web as a graph. That's the easiest one to talk about. Okay, so web as a graph, and if we think about all your web pages, your web is a directed graph. So every node in this directed graph is a web page, and the edge between them are hyperlinks, right? So if you have a page and it has a hyperlink point to another page, you can start to construct this graph. If you have 1 billion web pages, you have 1 billion nodes, and you have plenty, more than 1 billion links between them. So look at web as a directed graph. You have things like different pages, and they all link to each other with a hyperlink. So the broader question for this web as graph application is, how do we actually organize the web? You have lots of web pages. How do you facilitate the search? Because remember, in our recommendation system lecture, it's the same issue, right? When you start to have large data set, one of the most important thing is to help your user find the one they like. That's the recommendation system, right? So how do you help users to find web pages they want to find? So our first try, or the human's first try, is curated web directories. I don't know if people still know this. We still have a company called Yahoo. It used to be a much larger company than Google. So this is your first version, Yahoo. And on Yahoo's website, you have some way to allow you to search for web pages. But the really cool part is they have directories, and these are human curated. So someone look at web pages and put them into different categories. We don't really rely on human curated web pages anymore. I don't think Yahoo does it anymore, but we still have curated web directories called demos. So demos is open data. Right now you can go to demos and look at the different categories. And one thing that's really useful is now every web page under a category starts to have some meanings, right? So if you want to train a machine learning classifier, or just like what we did to get topics from a document, you can use demos as your training data. Oh, right. Sorry, we don't have the slides on Piazza. Give me 1 minute to upload the slides. Okay, you should be able to see the slides on Piazza. Thank you for reminding me. All right, so human curated web pages doesn't really work because you cannot really scale up to process 1 billion web pages, right? Think about how many people you have to hire. Second try. So the second wave of organizing the web is based on information retrieval. This is one of the really cool fields in computer science. So information retrieval looks at the problem of finding relevant documents in a small and trusted set of documents. Right, so think about if you have archived newspaper, archived legal documents, these are trusted set because you know you can trust all these documents. These are not like web. In information retrieval, it's usually look like this. So you have some documents, you have some way to index them, you generate the index. So index could be keywords, important keywords, or TF-IDF words. And when the user queries, the user will issue some query keywords. You compare them with top K retrieval of the keywords. Then you return the document. And you can do some training, very similar to what we did in content-based recommendation system for documents. You can train a decision tree for respond to a certain queries. The problem of this type of approach is web is huge, right? You have billions of documents full of untrusted documents, random stuff, web spams, etc. So how do you make information retrieval work on the web? It's impossible. So if you look at the information retrieval types of approach, early web search, these approaches would extract keywords from web pages. It could be from titles, from content, and it could be the keywords from titles will be more important compared to the keywords extracted from the content. Then we can use all these keywords to build inverted index. So inverted index look like this. This means if you are querying for banana, I will return you document 2. If you're querying the word what, I will return you document 0 and 1. Right. So these queries are matched with web pages by looking at this inverted index. And pages will be ranked by the occurrence of query keywords. So if a document contains many of the keywords, it will rank higher. But this type of approach cannot protect itself against term spam. I don't know if you guys still know this, but term spam was very popular. So the way term spam works is you can disguise a page as something that it is not about. For example, let's say you want to sell cars. You're a local car dealership, but you want to boost your rank of your web page. You want people, when they search for movies, they will be able to find your car page, right? And if you want to fight those information retrieval type of approaches, you would just add thousands of keywords movies to your page. But your actual content might be something else. Could be car sales, could be some other advertisement, and so on. And this way, the search engine looks at your content and they say, all right, this page contains lots of movies. When someone searches for movie, we should return this page. Also, when you are editing this HTML page, you can fade your spam word into the background, right? You just have lots of movies in your on your page and make them white font and make your background white so the user will not be able to see it. So if you do this, your spam pages may be based on also your spam page can be based on the top ranked pages. For example, if I just Google, if I just search for a page, say I use a keyword movie, right? And I take the first couple pages, I strip all the HTML tag. Now I have the content. I use those content, use white font as the same as my background and put them on my web page for selling cars. This way, no matter what the user queries, if I collect a lot of them, no matter what user queries, my content will be always similar to the top result. So my page will be highly likely to be returned on the first page. And this is a type of term spam as well. So in general, when we look at the web searches, there are 2 challenges. The first one is the web contains many sources of information, so we don't really know who we want to trust. And one of the heuristic or hypothesis that we are going to use or PageRank is based on is trustworthy pages may point to each other, right? If you have a link to other page and if we can trust this first page, that means we can probably trust the second page. Also, the second challenge is what is the best answer for the query newspaper? There's no single right answer. Well, search engine these days are really sophisticated. So it depends on where you query. If you query newspaper in Texas, you get a different answer compared to when you query the keyword newspaper in the UK, right? And sometimes these are based on location, based on the time when you issue the query, based on the historical query result and user behaviors and so on. So the trick is pages that actually know about newspapers might all be pointing to many newspapers, right? So if you look at these 2 tricks or assumptions, they both talk about links, right? Links between nodes. Now we are talking about a node is a web page. The second one is point to many newspapers, right? So the criteria here is many links. The criteria here is all linked to something. So you start to see the assumption of the algorithm is going to exploit the link structure in your data to help you find the most important nodes or the most important pages in the web. So that means we are going to rank our nodes in the graph, and we're going to rank them based on their importance, and the importance is based on the link structure. For example, we can safely say that all web pages are not equally important, right? USC domain compared to this blog, bob.com. If you don't know about this URL, this looks more familiar, and more other websites point to this website, so this should be more important. Also, there is a large diversity in the web graph, node connectivity. If you just look at here, this one is very popular, right? This one is not very popular, but this one is medium popular. So how do we rank it? How do we exploit the link structure? So let's look at some algorithms that can help us rank the pages, in this case, nodes in a graph based on the link structure. That's our link analysis algorithms. So in the link analysis topic, we are going to cover PageRank. That's the Google algorithm. And we're going to talk about one variant of PageRank, topic specific, so more personalized PageRank scores. And we're going to talk about web spam detection algorithms. All right, so let's start from PageRank. Originally, the idea of PageRank is to combat term spams, the pages that take other people's content or use movies 1,000 times in the content just to pretend it's about movies. So the key idea of PageRank is we want to rank each web page by their linkage, not just by the content. So by linkage, we mean we want to rank them by how many pages point to a page, and also the importance of these pages, right? Two criteria. USC.edu can be important because many pages point to USC.edu, and at the same time, your homepage can be important if it is pointed to by USC, right? Just look at here. We say USC is important because many nodes, many other pages link to USC. But if you look at your page, you don't have that many incoming nodes, right? Not that many people knows your web page compared to USC's web page, but yours can still be important because an important node point to you. So two things that will make a page important. This is important. So the PageRank algorithm is based on a random server model. For a random server model, we are talking about a random server of the web. The random server can start from any page, so any node in your graph. Then the random server will follow an outgoing link randomly and just traverse your node, just mimic a person who is browsing the entire web. A page is important if it attracts a large number of servers. So what would be the page that would be able to attract a large number of servers in this case? Anybody? Okay, so Chen Yuan says USC. If you look at here, just look at this graph. So I'm a random server. I can start from any page, okay? So let's say I start from here. And these are discrete time. So time 1, time 2, time 3, and time 4, and time 5, and so on. So at time 1, I am here. Where can I go at time 1? At time 2? Well, I can follow the links, right? So I can either go to USC or go to me. Okay, there are only two links. Let's assume that I choose them with equal probability. Let's say I end up at USC. Okay, where can I go next? Well, I can only go to you, right? And if you start from here, fake at time 1, where else can you go at time 2? We can go to all these fakes, right? And eventually, when you have more time, you might end up at spam because they all connect to spam. So for a node in this graph to eventually attract many servers at time n, that means first you have to have many in links, right? That way your random server will be able to reach you. Or if you don't have many in links, which is okay, but if you have an in link from a very important, like this one, this is very important, it already attracts many servers. So these servers on this node might choose to go to your page, right? So this way you become important as well and attract many servers. But mainly your servers, random servers, are coming from here, right? So this is the same as our two criteria. A page could be is important if you have many in links, or you have a link, a very important page point to your web page. So when we talk about PageRank is actually a score or a probability that a random server lands on the page. So eventually, when we talk about time n, if a page has high probability of a random server lands on that page, or we can call it a high PageRank score, that means the page is important. So the intuition is very simple. If a page is important, many other pages may directly or indirectly link to it, right? So that your random server will be able to find that page. So random server can easily find it. Your spam pages are less connected. Not that many people will link to a spam page unless the spammer create many pages to link to its own spam page. We're going to talk about that later as well. So spam pages are less connected, so less chance to attract random servers. Your random server model is more robust than manual approach. Manual approach, like the curated approach to figure out which page is more important. So think about your random server model as a collective voting scheme, because every server is rating, right? Eventually, when they stop and stay on one node, that's the node they vote for, and that node will become important if many people vote for it. So some example of your PageRank score, you have B here. B has a really high score, and if you look at B and C, they both have high scores. And can you tell why B would have a high score? B has a high score. Yes, great, Chen-Yuan, because you have many in links, right? Random server will be able to discover B based on all these links. Why do we have C as a high score one? Well, because B point to C, so B actually collecting lots of random servers, and these random servers can discover C, right? Because B links to C. No, so Jen says, Xiang says, because they link to each other. No, not because they link to each other, only because B linked to C. This one doesn't matter much. The most important one is this link. Because think about this. You have B has already attracted many random servers, right? So at the next timestamp, where are all these random servers going to go? Well, they can go to C, right? Because you have a link here. Then C becomes important. So there are some assumptions about PageRank and PageRank algorithms. The algorithm suggests that we have a strongly connected graph. In this graph, a node is a page, an edge is a hyperlink between two pages. And when we say strongly connected, this is a graph property. Strongly connected graph means every node is reachable from every other node. So for example, from A, you can reach any other node in this graph, right? You can reach B by here, you can reach D, you can reach C. From C, can you reach to every other node? Well, you can reach to A. Can you reach D? Yes. You can go to A and then D, right? Can you go to B? You can go to A, then B. So this one is a strongly connected graph. We're going to talk about two extreme cases of not strongly connected graph, and that's spider trap and dead end. But we're going to talk about that later. Let's assume that your web is strongly connected. Well, first of all, in what case you will not have a strongly connected web? Well, you can create a web page, right? You can say this web page contains your biography. Yao Yichang graduated from USC and did this and all that, right? But you don't have any hyperlink. And somehow USC's link to my page. So this is a dead end. So there's a question, can a node point to itself? Yes, a node can point to itself. You can have something like this. Okay. All right. Thank you guys for asking questions. So our random server model, remember I say you have random server that can start from any node and jump to other nodes at different time. At the beginning, your random server can start at any node, let's say A. So time 0, A. At time 1, your random server can go to B, C, or D with equal probability. And this is because A has 3 outlinks, 1, 2, 3. So the random server will just pick one and just go. And at next time T, let's say the random server is at B. If the random server is at B, the random server can go back to A or go to D, but now it's still equal probability, but the probability now is 1/2, right? Because you only have 2 choices and so on. So this is the random server model. And this model, the property, the random server model property is it's memoryless. That means where to go from node X at time T or time T plus X is not affected by how the random server got to X. So if your random server is at A, when the random server is choosing where to go next, it only cares about the outlinks at this time point. It doesn't really matter if the random server gets to A from B or C or other places. Okay, so that's called memoryless. So let's look at PageRank algorithm in more details. The PageRank algorithm tells us that we are going to use Linksys vote collective voting scheme to help us identify important pages. So pages is more important if it has more inlinks. Okay, so incoming links or outgoing links, not outgoing links. If you think of incoming links as vote, www.stanford.edu has this number of inlinks. The www.onelink.com only has 1 inlink. Right, so this one is not that important, but many people point to Stanford. Let me give you one example. Let's say someone queried Stanford, and I create a web page on this onelink.com to sell my car. But I want to target my web page to Stanford student. So what do? Well, I just add keyword Stanford and I use white color, so it got blended in. And I don't think this is enough, so I go to Stanford's web page and take their entire first page and blend it into my HTML page here. Okay, so the user still see my car, not all this content. In an information retrieval approach, if you just do a keyword search, you will find this page, right? Because I have lots of keywords of Stanford. I have exactly the same content of Stanford. So this one will have high rank. However, because I just created this page and nobody's linking to this page, but if you look at stanford.edu, many other websites already link to this stanford.edu website, right? So this one should have higher importance given that both my page and the Stanford page contains content about Stanford. Okay, so the first criteria is both my both my page and the Stanford page, they have very similar content. They all contain keywords of Stanford, things about Stanford. Now the search engine needs to decide which one they need to return. They want to return to a user when they search for Stanford. And in this case, based on the voting or the inlinks of the importance of a page, the real Stanford site will be returned because it has lots more inlinks than my one-page website. Also, not all inlinks are equal. Links from important pages will count more. So for example, if I say, all right, let me just create inlinks, I will create 30,000 one-page website, and they all point to my website claiming this is Stanford. Well, this is not, if you just look at the number, I have 30,000, the real Stanford page has 23,000, so mine could be more important. However, all these pages that point to me are not very important, right? None of the web would point to them, but many of the pages point to Stanford, might include the USC web page, might include Wikipedia or other important website. So that makes Stanford website more important, although it has fewer inlinks. So how do we formulate this question or this page rank problem? Each link has a vote, and the vote is proportional to the importance of the source page. Okay, we're going to see that here. But let's go through this first. If a page J with importance RJ, so has a rank J, has n outlinks, each link will get a portion of the importance, right? Think about you're distributing the importance or distributing the random servers. Page J's own importance is the sum of the votes on all its inlinks. For example, consider this graph. The page rank RJ is, J is here. What are the inlinks for J? Well, you have one from I, you have one from K, right? Only two. The importance of J is the same, equal to the importance of I divided by 3, because I has 3 outlinks, 1, 2, 3. And K divided by 4, 1, 2, 3, 4. Cool. Pretty straightforward, right? If you think about, if you think of the R number here is the number of random servers. And the number of random servers that would be on J depends on what? Depends on the number of random servers on I, and the number of random servers on K, and the number of choices they have on each node, right? So if I has 3 random servers and they only have 3 ways to go, you know that at the next point, the expected number of random servers that will be coming from I to J will be 1, because 3 random servers, a third of probability that you are going to choose the route I, J, so that'll be 1, right? And the same for RK, if you have 4 divided by 4, you have 1, you're going to contribute 1 from K to J, so that's 2. Okay, so if you look at this means we can start to define the importance or the rank for every node based on their inlinks and other nodes outlinks, right? If we look at the concrete example, you have A, you have M, and you have Y. So Amazon, Yahoo, and Microsoft. A vote from an important page would worth more. A page is important if it is pointed to by other important pages. We know this already. And we want to define a rank R for page J. It looks like this. The importance or the rank of the page J, Rj, is equal to the importance of every page that points to J, right? Every page that points to J divided by the outgoing degree of that node. So if you look at this, graph, how many nodes do we have? We have 3 nodes. So we have 3 nodes. That means we want to define 3 scores, right? So 3 scores here. We are defining the importance score for Y, for A, for M. Great. So how do we define the score for Y? If you look at Y's score depends on what? Depends on every node that point to Y. So who points to Y? Well, Y itself points to Y and A, right? So you have Y and you have A. Cool. And if you think about this, A score is going to be distributed among all the outlinks. And how many outlinks does A have? 1 and 2. Okay, great. A divided by 2. For Y, how many outlinks does Y have? 1 and 2, so divided by 2. Pretty easy, right? So for every node, now you can formally define their page rank or importance score. Yeah, so Y point to itself, right? Correct. Y is Y divided by 2 plus A divided by 2. It's also an outlink. So for Y, you have 2 outlinks. And how many inlinks do you have? You have 2 inlinks. If you think about the degree is 1, 2, 3, 4. All right, so great. This is our flow equation. Having an equation is not enough, right? We want to be able to solve the equations and figure out exactly what is Ry, what is Ra, what is Rm, so we can compare them. So solving the flow equations. This is our equation. We have 3 equations, 3 unknowns. There's no constant. This means we do not have a unique solution. What we can have is we can have solutions, but all these solutions will be equivalent modulo scalar factor. That means you have to have one more constraint. And fortunately, we do. That's this. Our constraint says the summation of all the page rank scores in a graph, or the importance score of a graph, should be equal to 1. If you look at this is very similar when we are talking about probability, right? When at the beginning, your random server can land on any nodes with equal probability. And eventually, if you think about this, if you look at this R scores and you say this is the probability that a random server will land on a node, right? You will say, and they should all sum up to 1 because the probability that the random server will land on a node is 1, and we just don't know which node. So let me say this again. This is the probability. You can look at this and think of this as a probability that the random server will pick Y at the end of time n. Let's say you jump for n times. And the probability of the random server will will end up at A is 2/5. Also, length at M is 1/5. Okay, so apparently Y and A has equal probability and M has less probability. Why is that? Let's look at the graph. So if you look at M, how many inlinks does M has? Well, M only has one, right? So you can M only rely on A for the random server. But for A, you do have an inlink from M. You also have an inlink from what? Y. For Y, you have an inlink by yourself. That means your random server might not choose to leave. It might stay. So you have yourself as an inlink, and you also have A as an inlink. So intuitively, you will be able to see that M has a smaller score compared to Y and A. So, all right, this looks easy, but in this lecture, we are going to talk about Gaussian elimination and other methods to solve this equation so that you don't, well, you can still use a library to solve this, but I'm going to show you how you would use Gaussian elimination to find out the result or the solution for this equation plus this. Okay, and the only reason we want to go into the details of Gaussian elimination is because I want you to be able to understand the complexity of different algorithms. Because this one looks easy because you only have 3 nodes. Your web page, your web has 1 billion nodes, so you cannot really do this. You have to figure out an efficient method. And Gaussian elimination methods, I think, should be your high school linear algebra material, but we're just going to talk about this method in terms of the complexity. All right, metrics formulation for a PageRank. So for PageRank, we're going to define a stochastic transition matrix, or you can just call it adjacency matrix. Stochastic transition is just a fancy name for transition matrix, adjacency or transition matrix. Suppose your page J has n outlinks. And if you have an outlink J to I, then Mij would be 1/n, right? Because you have n outlinks. Or if you don't have a direct link from J to I, your Mij would be 0. And this matrix is a column stochastic matrix because the columns sums to 1. So column stochastic matrix is just a type of matrix that has its own property that we can use. We're going to talk about this later. But if you are not familiar with the term column stochastic matrix, you're okay. So transition matrix. Let's just look at the example. This is your graph. This is your matrix. What does 0 represent here? You have A, you have A. So this means A does not have a link to A. Cool. 1/3. Right, A does not point to itself. 1/3 means A point to B because you have a value, you have a non-zero value. But why do we have 1/3? Well, because A has 1 outlink, 2 outlink, 3 outlinks, right? So they should have equal probability. A point to B, A point to C, A point to D. And let's look at the second column. Again, this column documents the outlinks of a node. In this case, we're looking at node B. So what is 1/2? B point to A, and this also indicates that you have 2 nodes. So the other one is B point to D. Okay, pretty easy, right? And you can easily see that it sums up to 1 because this is probability. A random server at A has equal probability to go to B and C and D, so 1/3 everywhere. A random server at B has equal probability to go to A or D, so 1/2, 1/2. Random server at C it will always go to A, so 1, right? If you look at here, C only has one outlink, and that's to A. So for our matrix formulation, we just talk about this adjacency matrix and sum up to 1. Now let's look at rank vector. This rank vector is something that we want to derive. This is the page rank or the importance of each node. This is a vector with one entry per web page because every node or every web page will have an importance score. So Ri is the importance score of page I. The flow equation can be rewritten as this. R equal to M times R. And I'm going to show you how this works here. But before that, let's take a 10 minutes break, come back at 7 p.m. And if you have any questions, feel free to leave it in the chat. I will answer them when I come back. Oh, now we have 20 people. We are growing. Good job. All right. We were here. Here. Wait, let me. I'm not very good at PowerPoint. Okay, we talk about the transition matrix, right? So here's your transition matrix. Still remember what the transition matrix? Each column is a node, and it should add up to 1. Why does it add up to 1? Because each of the value here indicate the probability that a random server at this node A would jump to other node at the next time point. So equal probability for every outlink, and it sum up to 1. All right, great. So we also talk about this PageRank matrix, well, vector. So this is your transition matrix. We say your transition matrix times multiplied by your rank matrix at T equal to your rank vector at T plus 1. So how does it work? So suppose, let's look at one example. Suppose your page J links to 3 pages, including page I. So we know we are going to look at column J, right? Because page J links to 3 pages. And we know we are going to find 3 non-zero values, 3 of them, and each of them will be 1/3 because you have 3 pages, and the probability of using any of the links is 1/3, equal probability. So let's say at the beginning you have a rank vector, the importance. Now, if you take the multiplication to generate this, the importance of I, this row, how do you calculate this row? It's a dot product between this and this transpose, right? So if you do a dot product between this row and this column transpose or this vector transpose, that means you are taking 1/3 multiplied by the importance of J, okay? Assuming you only have 3 nodes, 1, 2, 3, 1, 2, 3. When you're doing the multiplication, this 1/3 will multiply by the importance of J and sum up with the other multiplication to get this, right? So this is exactly what we did in our Amazon, Yahoo, and Microsoft example. The importance of I include a contribution from J, but only 1/3 of RJ because J has 3 outlings. So from this MR equal to R, we are going to look at a very important property of PageRank that's called the stationary distribution. So stationary distribution, or you can call it limiting probability distribution of the random server, is the probability destruction will converge eventually. That means when you do M, R, T to generate RT plus 1, and you do this over and over and over again, eventually RT plus 1 will be the same as RT plus 2. That means it doesn't change anymore. And to have this property, your graph needs to be strongly connected. so that it has this limiting distribution property. The requirement for this limiting probability distribution property is that your graph has to be strongly connected, cannot have any dead end and spider traps. And we're going to talk about what if this happens. But at least now you know you have a transition matrix that you can generate just based on your graph structure, right? This transition matrix capture all the links in your graph and the number of nodes, because the dimension is the number of nodes times the number of nodes. You also have some rank vector. And you can say at the beginning, we say the random server can be anywhere with equal probability. So let's say if your vector has 3 nodes, it should be 1/3, 1/3, 1/3. At the beginning, equally important. Okay, and you take m times r, you generate a new r. Then you take the new r, you just do m times the new vector, you generate another vector, and you keep doing this. Eventually, it converges. That means this vector doesn't change anymore, and you have your solution. But this is actually more complicated than what I just tell you. So let's look at how we solve this nv equal to v. So from nv equal to v, or if we write it like this, r, the r vector, equal to the transition matrix times your r vector with the limiting distribution. That means r doesn't change anymore. So what does this r vector mean to m? Remember what we did before with your eigenvector and eigenvalues? This r is actually your m's eigenvector, right? So if you take m, a matrix, multiply this matrix by a vector, and you does not change the vector's direction because it's still the same vector, and you have an eigenvalue of 1, this r is the eigenvector of m, and 1 is the eigenvalue. So now we know the PageRank vector R is an eigenvector of the stochastic web matrix or a transition matrix M. Your R is M's principal eigenvector or first eigenvector because it has an eigenvalue of 1. And we know that the largest eigenvalue of M is 1 since M is a column stochastic matrix. This is just a property of a column stochastic matrix with non-negative entries, and every column sum up to 1. We also know that R is unit length and each column of M sum up to 1, right? That's the basic property which is defined for your PageRank vector and for your M matrix. We're going to look at one example of this. So now we can find R based on a transition matrix using 2 methods, power iteration and principal eigenvector. And we're going to look at these 2 methods in details. First method, power iteration. This one is super easy. You start by looking at your initial R vector, and the way you initialize is you just give everybody equal probability, right? Because the assumption is your random server can be anywhere, and this is your graph. Based on the graph, you know you can write your M, right? Your transition matrix. So how do we generate the next PageRank vector from the initial one? Well, we just take M, multiply this to derive this, right? This tells us that all the random servers is going to follow the links in your M and then land on some node. And what is this vector? This vector tells you that at time 1, so this is time 0, time 1, at time 1, the probability of a random server will land on node A is much higher, well, not much higher, it's higher than all other nodes. Do you stop here? Well, you don't. right? Because remember, MR equals to R because of the limiting distribution property. That means these two R should be the same. So you just multiply M again on this vector, generate a new one, again and again and again, you generate a new vector, and eventually you stop. So you usually stop when little changes between iterations. To be able to follow this constraint, little changes is not enough. You want these two R to be identical, right? But very often, these little changes doesn't really matter much because you only want to find the most important one. It's the absolute value of the PageRank is not very important. So in practice, we would just do 50 to 75 iterations for web transition metrics. It's already a lot because your transition metrics will be, let's say, 1 billion by 1 billion, and your PageRank vector is 1 billion by 1, right? So this is a lot of components to compute. So let's look at one example. Yahoo, Microsoft, and Amazon are old friends. Based on this graph, we can write this transition matrix, column stochastic, every column sum up to 1, right? Let's look at first column. Y goes to Y and goes to A. Great. And equal probability. Okay, cool. Now we just verified this transition matrix is correct. What we want to compute is the PageRank vector. So we are saying that based on the stationary or limiting probability distribution, your PageRank vector eventually will be the same as the transition matrix times your PageRank vector, right? These two should have the same value. Looks like this. Power iteration method. Oh, so this is exactly what we did before, right? When we did this, we did not have this transition matrix. But if you want to generate this function, you can just say ry. So ry is here equals to what? First row, first column. So 1/2 times ry here. 1/2 times ra here, and 0 times rm, right? That's your ry. So that's your first equation here. Okay. So how do we do power iteration? It's a simple iterative scheme. Suppose there are n web pages. You just initialize your first PageRank vector with equal probability everywhere. So there's a transpose here because you usually write your vector like this, right? You start to iterate the process. R k plus 1 at time k plus 1 equal to the transition matrix times R at time k. You're going to stop when these two vectors are very similar, so the difference between them are very small. So this notation is saying that we are going to use L1 norm. So you're going to compute the difference between corresponding components and sum them up. You can use all other different norms or Euclidean distance between two vectors to help you set this criteria. This is not extremely important. Just need to know that you have to have a criteria. So power iteration. Your PageRank vector, you start from equal probability everywhere, and then you do this. You have this, you do it again, this, again, again. Eventually, it doesn't change anymore, and this is your answer, right? So power iteration, very simple. You just keep multiplying your PageRank vector by your transition matrix, and then you're done. So the second method of solving this MV equal to V is by finding the eigenvector of M. So let's look at one example and the property of eigenvectors again. So MV equal to lambda V. In this case, this is a scalar. That means V doesn't change direction, right? Because this is the same V. And in this case, your lambda is the eigenvalue of V, which is the eigenvector of the matrix M. We know that M is a stochastic matrix. Each column adds up to 1. And for a stochastic matrix, the largest eigenvalue is 1. We can verify this. We will do that on the next slide. And the corresponding eigenvector has a name. We call it the principal eigenvector. And let's look at the proof. So this is our transition matrix. Cool. This is the way we calculate your eigenvalues and eigenvectors. Well, this is the way you write it. You're not calculating it yet. So if we reorganize this equation, you move your V to the same side, it becomes this, right? So M minus lambda, and because lambda is a scalar, you want to do this operation, your lambda needs to multiply by an identity matrix. If you don't remember your high school math, it's here. So this will need to be, this will equal to 0, right? This left-hand side. And also, in this case, we know that your vector V is not a null vector. So the only possible case that this left-hand side term is 0 is when the determinant of this matrix is 0. Okay, so this is just some matrix property. So how do we calculate the determinant of a matrix? Let's look at the solution. This is the matrix. Why do we have this? Well, this is M minus lambda I, right? I is the identity matrix and M is here. Let's verify it. So the first element in your matrix M is 0, M minus lambda I, and identity matrix has a 1, so lambda times 1 is lambda, and 0 minus lambda is minus lambda. Okay, cool. Let's look at the second element. 1 over 2. So M minus lambda I. What is I? I has a 0. Lambda times 0 is 0. So, okay, it doesn't change. Cool. So now I verify 2 elements. I assume this entire matrix is correct. Let's calculate the determinant. So to calculate the determinant of a matrix, this is also your high school math or your junior high. You pick a column and a row if it's not a 2x2 matrix. If it is a 2x2 matrix, you don't have to do this. And I will show you once, but you should be able to do this by yourself. All right, so it looks like this. If you have a 3x3 matrix, you pick a column and row and you work on there. So here you pick a column and row. Let's say we pick or a row, you pick this column. You pick this one because it has more zeros, so less things to do. So how do we do this? You pick this column, and for the non-zero element in this column, for example, 1, you block here, you block here. Now you reduce the matrix into n minus 1 times n minus 1 dimension. So you have 3x3. So 3x3, you write it here. Okay. Let's verify. 1 over 3, 1 over 3, 1 over 3. Yes. 1 over 2, 1 over 2, minus lambda. Cool. Okay, great. And now this element is 1, so you have 1 times this, and you have to decide on the sign. So how do we decide on the sign? 1, 2, 3, column number 3, row number 1, 3 plus 1 is 4. 4 is an even number, so this is a plus sign. All right, cool. So next one, 0, we ignore 0 because if you put a 0 here, you don't need to calculate the matrix, right? So let's look at this minus lambda. Again, we block this row, we block this column. Now you have a 3 by 3 matrix. Here should be here should be here. Awesome, right? And you have to have a minus lambda here because this element is minus lambda. And now you have to decide on the sign. So which column is this? 3. Which row? 3. 3 plus 3 is an even number, so it's a plus sign, right? So you don't have to change the sign here. Awesome, great. So 4 by 4, now you reduce it to 2, 3 by 3. What do you do next? Well, they still are not 2 by 2 matrix, so you have to do this again. So for the first one, you pick a column or a row. Let's pick this one because you have a 0. If you pick this one, you have lambda. And you have what? 1 over 3, 1 over 3, 1 over 2 minus lambda. Okay, cool. Now you have to decide on the sign. So minus lambda is at column number 2, row number 1. 2 plus 1 is 3. 3 is an odd number. So you have to put a minus sign and you have minus lambda. You change the sign, right? So now you have lambda. And you do this for 1 over 2 also. And for this matrix, you do the same. You split that into 2 matrices. Are we done yet? No, but we are very close. When you have a 2 by 2 matrix, you can calculate its determinant by just taking this times this minus this times this, right? So you don't have to split the matrix again. Since you all have all the 2 by 2 matrix, you can just calculate them and you're going to have this. Reorganize all the terms, reorganize them again, reorganize them again. This is your final equation. This is the determinant of that matrix. Awesome. Lots of steps, but now you have this equation. All right. So if we say, remember this, our original goal, we want to be able to show this equal to 0. This is the determinant. This equal to 0 means your lambda could be 0, or your lambda could be 1, or your lambda could be 1 or minus 1 over 2, right? So yeah. And because you have a square here, so you actually have 2 eigenvalues of the same value, minus 1 over 2. And I just show you that in this case, your largest eigenvalue is 1, right? That's what we want to show originally. We took a lot of steps to show this, but just to make sure that you know, we can use 1 here. Cool. All right, so based on our calculation, the problem now becomes solving this, right? Because originally you have this. Now we show that this lambda is 1, this is 1. So we want to solve this to find V. To do this, in our graph partition lecture, I just tell you that you can use a math library to find eigenvectors, right? In this case, you can as well. But let's look at Gaussian elimination that can help us to find the eigenvector V so that we can compare the complexity of this power iteration method and this finding eigenvector to solve MV equal to V problem. All right, Gaussian elimination. Again, this is also your high school math, linear algebra, I believe. So this is what we want to solve. This is your M. So you can rewrite it like this. right? This is M minus the identity matrix. Remember, identity matrix has 1 in the diagonal. And since you have M minus 1, you have minus 1 in the diagonal. This is your page rank vector, or the eigenvector you are looking for, and equal to 0. Cool. So Gaussian elimination is this. For your Gaussian elimination, you take your matrix and you want to simplify it. And the way you simplify it is your goal is to have leading ones for every row and to have as many zeros as possible in the matrix. So how do we do this? We start from the first row. To make it a leading one, you multiply -1 for every component in the first row. So it becomes this. Cool, right? Now you want to make lots of zeros. And the way you can do, the things that you can do is you can do row operations. You can take your first column, add it to the second or other columns, and make some of the components 0. But remember, we are saying that we want to make the first, the leading ones 0, except with the 1 has a 1 here, with the first one has a 1 here. So what you can do is you take the first row, multiply every component by -1/3, and add it to the second row, right? In this case, it will become 0, because 1 times -1/3 is what? -1/3, and 1 -1/3 at 1/3 will be 0. And you do the same for this column and this column. You have all the zeros. But remember, this is a row operation. So for your second element, you still need to multiply it by -1/3. So it becomes 6, 1/6, and you need to add 1/6 to -1. That's why you have -5/6. Okay, cool. But at least for now, you are done. For the first row, you have a leading 1, and every other rows has a 0. Okay, so what do we do next? Remember, I said we have to have many zeros and many leading ones. So let's make this 1. So how do we make it 1? Well, the same thing, like what we did for the first row. For every component in your second row, we just multiply by -6/5, right? Then this one becomes 1, and others will change value. Cool. What do you do next then? You want to make all this 0. So 1 times this row, entire row, times -1/6, and add it to the second row. And you have this 1, or this entire row, times -3/2, add it to the last row, then you have this. Awesome. What's next? Make more ones and zeros, right? So now you want to make this 1. Make this to 1. Now this becomes -1, and you multiply a value, add it to the last row. This one becomes 0 and 0, and cool. You're almost done. You can actually, so now you have many zeros and all the leading ones. You can actually do more because you want to make more zeros. So you can take this row and add to other rows and make more zeros. Okay, so eventually you are going to have something like this if you do your Gaussian elimination properly. But what does this mean? If you look at this, now you started from this to this, it becomes extremely easy to solve. So still dot product or matrix multiplication, this row times dot product, the transpose of this column, it will be V1, right? Minus 3 over 2 V4 equal to 0. Cool. And you do the same for the second row. This one will be V2 minus V4 equal to 0. V3 minus V4 equal to 0. And don't forget, we have our probability distribution constraint that everyone should sum up to 1. And based on these four equations, we can solve for all the V's. And this is your eigenvector. All right, cool. So now I show you a couple of things, right? So at the beginning, we talk about MV equal to V with the transition matrix. You can define the PageRank vector. And because of the strongly connected graph property, limited distribution, we can say eventually this V will not change anymore, no matter how many times you apply, you multiply N. And to be able to find this V, we have two solutions. First one is power iteration. You just do this operation many, many times to see if it will stop changing. The second solution is to use Gaussian elimination to find eigenvectors for M, and that eigenvector has an eigenvalue of 1, right? I'll show you the determinant and polynomial characteristics. All right, so for power iteration, the complexity is k n squared, because every multiplication will take n squared. Your matrix is n by n. And we do have a k here because the k is the number of iterations. For Gaussian elimination, the complexity is n cubed. Why do we have n cubed? Remember, you are always trying to make a row that has a leading 1, and every other row has zeros everywhere, right? So for the first row, when you do this operation, you have to do n squared. That means you have to process every element. When you are moving to process the second row, now you don't care about the first row anymore because you have the first row has a leading 1. From the second row and below, you are going to do the same process. Make the second row a leading 1 and everybody else has a 0, so you are going to handle n minus 1. And so on, right? So then you have from n minus 2, n minus 3 until 2. And this number series, I think we did this last time for the stream data lecture. This is n approximately n cubed. So your Gaussian elimination has complexity of n cubed is actually much more computational expensive than power iteration, because for power iteration, you're looking for an approximate value. Your k is 50 to 75. And here your n could be 1 billion, right? Both cases, your n could be 1 billion. All right, cool. Any questions? So based on what we have talked about, that's everything you need to know about PageRank. But there are two extreme cases, spider traps and dead ends. So remember, we talked about this stationary distribution property that makes your MR equal to R. So in general, when we are looking at your random server at time t+1, your random server follows a link randomly, uniformly at random. That means this is the probability of your random server at time t. If you take your transition matrix, multiply it to this time t vector, you have your t+1 vector. Suppose the random walk reaches a state that your t+1 is the same as pt. Then we call this the stationary distribution of the random walk, right? We covered this already. And in this case, your r is the vector is the stationary distribution for the random walk. And for this random walk or stationary distribution to exist, we say that for graphs that satisfy certain conditions, the stationary distribution is unique and eventually will be reached no matter what the initial probability distribution at time 0 is. So in all our previous examples, we all assume that at the beginning you have equal probability. You have exactly the same value for every component in your PageRank vector, but it doesn't have to be that. If your graph is a strongly connected graph, eventually once you do this m times r, a lot of times it will converge and you have this limited distribution probability, and your random vector will not, your PageRank vector will not change anymore, no matter how many times you multiply this m. But this strong assumption do have two problems for handling web graphs. The first problem is some pages has dead ends, and dead ends means there is no outlinks. So like this one, right? So this graph is not strongly connected because you cannot go from this node to any other node. Your random walker has nowhere to go if they land on this dead end, and these pages, this type of pages can cause your importance or probability to leak out because people will stay here and die. The second problem is spider traps. So in a spider trap, all outgoing links are within a group like this. So if you look at this graph, if you're a random server, you enter this trap, you have nowhere to go. You can only travel within this trap and you're not going anywhere. So your random servers get stuck in the trap. Eventually the spider trap will absorb all the importance. That means eventually all the random server will come here and they will not be able to leave. And here becomes 0 important, and this one becomes very important. So let's look at a couple examples. Give me 1 minute. All right, so here is a spider traps example. Our old friend, Yahoo, Amazon, and Microsoft. And here you can see your Microsoft is a spider trap. If you enter Microsoft, you can only stay at Microsoft because you come back, right? There's no anywhere else that you can go. So if you look at the transition matrix, it looks like this: column M indicating the outlinks. M does not go to Y, M does not go to A, M stay at M. So if you write it as R equal to MR and write it in the function as the equations, a set of equations, this is your equation. And if we do power iteration, eventually everybody else will be 0, M becomes 1. Okay. All the PageRank scores got trapped in node M. This is actually pretty easy to understand. If you think about your random server, you have equal probability to choose any node, but you have to follow the links. If you are in A, you can jump to M or jump to Y, right? Equal probability. If you choose M, you are not going to come. If you choose Microsoft, you are not coming back. You're going to stay in Microsoft forever because there's no outlink. On the other hand, if you choose Yahoo, you still might be able to come back, but with some probability you will choose Microsoft. So eventually everyone will choose Microsoft and never leave. So the solution for solving this problem, at least the Google solution to solve the problem, is this: teleporting. That means at each time step, each time when the random server is making a choice on where to go next, it has a probability beta to follow a link at random. So still, this is following the original transition matrix, the outlinks at random, but it also has some probability to jump to some random page. That's why it's teleporting. And the common value for this beta or damping factor is in the range of 0.8 to 0.9. That means you have let's say 0.8 probability to follow the original transition matrix and 0.2 probability you are going to be teleported. So your servers will be able to teleport out of the spider trap with some probability, right? So this is your original graph with a spider trap. With teleporting, it looks like this. Each node, now you have some possibility to be able to go to all other nodes. So let's look at the graph again. Your original graph, your M, right? Your original transition matrix. And this is teleporting, right? With teleporting, now if you're in M, you can go to Y, you can go to A, you can also stay with M, but you already have that link. Y, originally you do not have a link to M, but now you do. You can go to M, you can go to A, and you can go back to yourself. All right. So that's your teleporting transition matrix. So again, teleporting transition matrix is a transition matrix. So every column will sum up to 1 and with equal probability, right? So this one will have the same value everywhere because you are teleporting, you have the same value everywhere. But this is your new transition matrix, the summation of these two. What does this mean? You have 80% of the probability to follow the original transition matrix. You have 20% probability to follow teleporting. So if you do the calculation, you would be able to generate sorry. If you do the calculation, you will be able to generate this matrix, right? This matrix, this new updated transition matrix, include the possibility that a random server would teleport. Then you can do power iteration again. And you are going to have your page rank vector. Right? Pretty cool, right? So you are forcing this graph to be a strongly connected graph. Now you can go from every node to every other node by teleporting. So let's look at the matrix formulation. Suppose you have n pages. You consider a page J with some outlinks. And this is our original transition matrix. The random teleport is equivalent to adding a teleporting link from J to every other page with equal probability. So what is N? N is the number of nodes because you want to be able to teleport to any nodes with equal probability. And what is 1 minus beta? 1 minus beta is the probability that you would teleport because you still would might follow the original transition matrix. So this reduces the probability of following each outlink in the original transition matrix. It was originally this, now it becomes 0.8, 0.9 times the original probability, okay? And we also call this taxation. This means we are going to tax each page some fraction of its score and redistribute it evenly, right? This is the redistribution part because you are asking your random server to teleport. And this is the part that being taxed because original value is like this. This is the value after tax, so smaller contribution. So we call this also, we call this teleporting also as taxation as well. And this taxation help us to deal with spider traps and dead ends. I don't think we covered dead ends yet, but it helps us to cover both of them. It allows the servers to jump to a random node, and this jumping is called teleporting. So your new vector is equal to damping factor, 0.8 probability, for example, that the random server will follow the original transition matrix times the PageRank vector from the last step, plus some probability that the random server would teleport, and equal probability everywhere, right? So in the previous example, remember we have this 0.8 matrix plus 0.2 matrix. We generate a new matrix. Then we use new matrix to do teleporting. Sorry, to do power iteration. This is exactly the same as this. It's just different way to write it, right? This way, we are looking at this two part as one because it's easier to calculate. This way, we are looking at the original transition matrix versus the teleporting part. This helps you to understand what are the things that has been text and what are the teleporting probability. So this makes the graph strongly connected, like we said, because now you can teleport. So let's look at the text. This is your original transition matrix. This is your vector, PageRank vector at zero time. Your PageRank vector at time 1 equal to original transition matrix times 0.8, 80% probability that you are going to follow the original transition matrix, and your V0 plus 0.2 chance that you are going to teleport. You are teleporting, so you are going everywhere with equal probability. And sum them up, it becomes this. So let's look at detail. Originally, your C is a spider trap, right? If you go to C, you are not going to leave. So let's look at how C changes over time. This is your C, original PageRank for C. Now your new C, based on the random server following the original transition matrix, and the contribution to new C based on the teleporting. So how do we generate this? This has contribution from C itself because of this thing, also from A and from D, right? So from C, the calculation is here. 1/4 is going back to C itself because C has no other index, times 80% probability we are going to follow the original transition matrix. This is 1/5. For A and D, the contribution to C is 1/6. So why do we have 1/6? Well, A has 3 outlinks, D has 2 outlinks. So 1/3 and 1/2 times 1/4, because originally they are both 1/4 PageRank, and times this 0.8 probability of following the original transition matrix, you have 1/6. Okay, so 1/6 plus 1/6 plus 1/5, you have 11/30. So this is the contribution from following the original transition matrix. And you also have 1/20, that's this, right? The teleporting, because other nodes can teleport to C as well. So eventually your C is going to have 25/60 for your next V. So this is V1. All right, we're going to work on this next Monday. Thank you, everybody. If you have questions you can come to my office hours in 10 minutes. If you don't, or if you're watching the video, I hope you are still reading your textbook, work on your assignments, and prepare for your quizzes and the comprehensive exam. Also, since the project is out, make sure you work on your project as well. Okay? All right, have a good weekend. I will see you next Monday. Good luck. If you're coming to the office hour, you can stay, but I will be back in 10 minutes at 8 p.m. Hello, I'm back. All right, any questions? Oh, we do have a new friend here today who don't usually come to my office hours. So how about let Yoshan start?
So you recognize all of us, right?
Yes, of course. We're almost at the end of the semester. Or maybe Yoshan is just forget to log out. I
Makes
think
sense.
maybe is all right. Okay. All right. So Shang, you can start. You have any questions?
Me?
Yeah.
Yeah, I just have a quick question on the 3 days because you said the poll has not blah blah blah. To be clear, you cannot use your 3 days after the end of the semester.
Right. So that's not really about that's really not my decision because the university require everybody to submit their assignment before the last day of the class.
Oh,
Right.
really?
The last day of the class is April 30th.
Okay. But we can use those extra 3 days for final project.
You can because that's final project.
Well,
Because
but
if you use that for final project, that means we are going to what? We are going into your, we're not going to have time to submit your grade because that's your final date. If you use it and we are going to have one more week to grade it, it just take too much time.
so that means 3 days can only be used before April 30 or
Yeah,
29.
30th.
Okay. Yeah, I think that's all my question. Thank
Cool.
you.
And because I think we already extend your last assignment for a couple of days. So maybe
3 days?
3 days is not very important because it's due on Wednesday or Thursday. Thursday. Usually it's due on Monday.
Okay. Yes, so that to be honest, the 3 more days does not make a lot of help because
Well, think about this. If your last assignment is due on a Monday, your 3 more day will help you,
okay.
right? And because we extend that, so it doesn't really help you much, but still you can use it
Okay,
at least 1 or 2 days.
I see.
Because now instead of submitting on a Thursday, you can submit on a Friday, something like that.
Yeah, true.
Okay, all right. Chen Yuan, any questions? Or Jin Chen?
Hi, Professor. Again, I got confused about the free late days. So we cannot use it to extend our deadline until May.
No. You need to submit your assignments, all of your assignments before the end of the semester.
Before the end of this month,
Yeah,
the April.
I think April 30th is the end of the semester. All right, let me just double check.
Our
USC.
final project is gonna end on May 7th, right?
Yeah, because final project is your final. It's not an assignment because we don't have a final.
Okay. Okay, because I was thinking about uh we still can extend our the last um assignment until the weekend until to the May
Yeah,
1st.
we can't because the weekend is your study days. The university rule is very clear.
Okay.
We cannot
Yeah.
ask you to return homework on the study days.
Yeah. Thank you.
Sure. Chen Yuan? Are you guys doing well in the assignments?
No.
Which one?
I almost gave up on assignment 4 because I don't have time. So yeah. And on assignment 3, I got 1 point deduction because I had a typo in task 1, and another 1.5 deduction because the required RMSE is 1.1015. But my score is 1.016.
Oh, but did you know that before you submit?
Right before I submit, my score was 0.99, so I thought it was safe.
What happened? Oh, because of the blind data set?
I guess so. I went to the office hour and asked for the TA to run it again, and she did so, but the same score. So yeah.
Wait, I'm confused. So you're saying that running on the same data set, but different scores?
No,
or
no,
different data set?
because when I got the score, I went to the office hour and asked the TA, can you run my script again to see if it has another result, but the results are the same, 1.016. So
Do you know what happened?
I don't know.
Well, you probably should figure out, right? You can run it locally. You don't have to run it on Vocarum to figure this out.
Yeah, I
Since
know.
since this is your assignment 3, so you are going to build your final project based on your assignment 3. It'll be nice to figure this out.
Yeah, I'm trying to figure that out.
Oh,
How
by
about
the way,
others? Do you guys? How's your assignments?
I have a question for the final project. Usually for the previous semester, what is the RMSE the students will get finally for the final project?
Can you say that again?
Because our final project is going to be compete on our RMSE. Based
Right.
on RMSE, we will get ranked. So usually, I mean, for the top 3 or top 10 of the session, what RMSE do they in previous semester do they achieved?
Oh, I can tell you from last time we did this. I think it's the same data set, but last time when we did this, your TA has an RMSE of 1.1.
1.1.
Let me see. Full semester. Okay, your TA has an RMSE of 1.18.
Okay. That's already more than the requirement in our homework 3.
Yeah, so maybe that's a different data set.
Yeah, you're right. Yeah, probably a different insight.
But I can tell you from last time, your TA has 1.18, and if you beat your TA, 10% low, if you beat your TA within 10%, well, I shouldn't say beat your TA. If your RMSE is 1.29, that's 10% more than the TAs, you have 1% bonus. So that 1% is actually a lot. That means your final score, if it's 85, it becomes 86. And if you beat your TS score without that 10%, you receive a 2% bonus. So 85 becomes 87. If you beat your TA, then you are qualified in the final competition. So in that final competition, first place, the entire class has a 4% bonus. So if your original score for the entire class is 85, now you have 89. Second place, you have 3%, so 85 to 88, 85 to 87, and so on.
Yeah,
So-
I see.
That's a lot of bonuses.
Yeah, I mean,
Sorry, can
Sorry.
we use the external packages when doing the project?
Oh, your project, you can use any packages you like.
So the key point is how to implement the hybrid, like the hybrid part, not the recommendation system itself, right?
Well, the hybrid part is the recommendation system, but I guess you're saying that not implementing the individual component of the
Yeah.
The
So you
hybrid.
don't have to like implement from scratch. You have to use, you can't use packages just to
Yeah.
yeah, just to find a way to combine them to make it hybrid.
Yeah, but we're going to test it on a blind data set that you don't have. So
Okay.
if you tune your model based on the training data set, it will not work well for the blind data set. So I can tell you the reason why we really need a blind data set, because in one or two semesters that we did not use blind data set, some student will just read the test file, put them in the code, and have a very low RMSE. We only know this because we look at the code and someone has like a crazily low RMSE, and we don't want that to happen. So we are going to test it with blind data set. But I
Okay.
think that's general too. Your system needs to work on blind data set.
Okay. So if say if I decide to use the packages, there's nothing, I mean, there's really nothing to borrow from my homework 3 because I implement from scratch, but now I don't need to, right?
You can still do it. You can still implement it from scratch.
But
Because
there's
I think that the collaborative filtering will be the same. It will be one
Okay.
component in your hybrid system.
Okay. Okay, thank you.
But make sure you check with the TA to see what are the packages you can run on Vocarium. I don't know if they support all packages.
Oh, so we can only use available packages on the Vocarium.
Right.
Okay, got it.
All right. Any more questions, guys?
Yeah. For assignment 5, let me think about it for a minute. Yeah, I have some. I honestly don't know how to generate the CS,
What do you mean?
because when we have a few DS, right? We have a lot of points left.
Right?
So do we just randomly pick a point as a centroid and detect other points around?
You can run a k-mean. So okay, let me rephrase your question. Now you detect DS already, right? And you have
Oh.
lots of,
You mean running a k-means on the rest of the points?
yeah. Then you can find clusters.
Okay, so the way we define DS is not necessarily need to be the same as the way we define k-means.
No.
Okay. Oh, that's smart. I see. Yeah.
So you're just going to use k-means multiple times and use it in a different way and set the k different way to find DS, RS, and CS.
Can you go more detail?
Sure. So think about this. Now you have lots of data points. You have lots of data points, right? And if your goal is to do to have 3 clusters, let's say you do k-means, k equal to 3. What does it give you? Well, it will give you for sure 3 clusters.
3 clusters, yeah.
Right? But within each cluster, now you can use any metrics you like. I'm sure you know some way to do this, but I'm just going to tell you on a higher level that for each cluster, the goal is to be able to find the data point around the cluster center and call this the DS,
Yes.
right? Because this first batch of your data point, the distribution is not going to follow the data distribution of the entire data. So you might have some bias in this data. So you don't want all these points that far away from the center, right? You just find the one near the center and say this is the DS. Cool. Now you have the DS. Now the next problem is with all these other points, how do you find CS and RS? Right?
Yeah. For example, how do we define the number of K?
Okay. So remember for CS and RS, what is the CS and what is the RS?
The CS is the points nearby the DS, but they're not close enough.
No, it's not nearby the DS. It's the points that are close to each other.
Yeah.
Right?
Or close to each other.
So now you have to do k-means again, but you have to carefully choose that k. What does it mean carefully?
I don't know.
Remember your k-means result. In our k-means lecture, we talk about using this elbow point to find the right k, right? When you are at the right k, each cluster will be compact.
Okay.
Right? So if you don't want to do elbow point, you can just you can just try it. You can just say, all right, let me just try k equal to 200 and see how many of the clusters has 1 point. If you only have 200 points here and you do k equal to 200, then you only have 200 clusters. Each cluster has 1 point, and everyone will be outliers. Is that a good result?
Not really.
Not really, right? You're not saving anything. So you want to have some CS, but at the same time, you want your CS to be compact.
Yeah.
So how do you evaluate compact? How do you set the K? I'll leave that to you. But you're going to run k-means again on all these other points.
Sure.
So when I say empirically on Piazza, I meant you just take some sample and just try different k, right? If you want to use elbow point, you can. You just k equal to 1, k equal to 2, k equal to 3, k equal to 300, and see which one is more compact, and then you have your good k.
Yeah. And another question, because k-means are very hard to verify if it's a valid function. So can we just discuss with teammates or classmates? For example, we both use the same data set, and then we generate the same number of k, and then we compare its
Oh
output.
yeah, of course you can.
Okay.
But the only criteria is you don't show each other your code.
Okay.
Other than that, everything is
Sounds good.
Everything is okay.
I do have another question for this.
Sure.
So when you finish the BFR algorithm, so the only thing you have is your DS summary, right? You don't have the all the points because you discarded them.
You don't
right?
have all the points, right?
Yeah. So let's say you have 10 DS set, and then each of the DS set has 3 components, the n sum and sum square, right? So
Right.
then how do you like?
How do you know the final class assignment for each data point?
Yeah, so do you like compute the centroid for each one, and
Yeah,
then so
you can do
basically
that.
okay, so basically you compute the distance again and then assign the points to the nearest one.
Yeah.
Okay.
Yes.
Yeah. So I'm just want to make sure that I don't have to keep the information of the coordinates of each point when I doing the BFR.
Yeah.
Yeah. I mean, I assume that's the point of using BFR.
Yeah.
Yeah. Okay.
All right. Great.
See you next week. Peace.
Thank you
Bye.
guys. See you next week.
Bye.
Work
See
on
ya.
your assignments.
Thank you.
Bye.